So far, all of our classes have been about OpenMP and multi-core, but today we leave that world behind and we go to the second of four parallelisms. This one is called single instruction multiple data, or SIMD, and this is still on the CPU. Okay, why do we care about this? We care about this because this is a fast way to do things with arrays of numbers. We can multiply two arrays very quickly and put them in a third array, or we can multiply two arrays very quickly and sum up the products. And we're going to do this faster because we can do more than one pair of multiplies at a time. And there are a lot of problems in science and engineering that end up this way, things like convolution, Fourier transform, power spectrums, or autocorrelation all involve multiplying a signal times something, arrays, and doing something with it. So this has some really interesting ramifications. Intel got the ball rolling in 1996. They created something called MMX, and MMX let you multiply not one pair of floating point numbers, but two pairs of floating point numbers simultaneously. Okay, and so you could work your way through a stream, a signal, very quickly, and that's why Intel did it. You know, MMX stands for multimedia extensions, and they were doing it for streaming audio. Well, and that was successful, and in 1999, they created SSE, which was four pairs of floats at a time. And since then, there have also been something called AVX, which stands for Advanced Vector Extensions. That'll do eight at a time. And in 2013, they came up with something called AVX 512, which will do 16 at a time, which is really interesting because that's one cache line. 16 floats, that's one cache line. 16 floats, that's another cache line. Multiply them together, that's 16 floats, and that's another cache line. So in fact, you can bring in a whole cache line, boom, multiply it, and write it out again. Not all hardware has AVX or AVX 512, but all hardware, pretty much all hardware, has SSE. And so in your project 4, that's why we're going to use SSE. Okay. Intel has also announced something called AMX, Advanced Matrix Extensions. And it looks like what they have in mind is sort of like SIMD, except for 16 by 16 matrices. This is pretty cool. I can think of a lot of good math reasons to want this. I can think of machine learning reasons to want this. So anyway, this is very cool. They're billing it as an AI acceleration engine, which sort of gives it away that they expect this will be useful for machine learning. And I think this is very similar to the tensor cores on the NVIDIA GPUs. All right. How does normal non-SIMD multiply work? This is an assembly language instruction. And in English, what this says is multiply R1 times R0 and put the result back in R0. And in a hardware diagram, this is how it would work. Register 0 would give its value to the multiply unit. Register 1 would give its value to the multiply unit. The multiply unit would multiply them together and put the results back in register 0. Okay, the SS, well, one of the S's stands for scalar. Okay, and the other one stands for, well, short. It means a float, not a double. Okay, now along comes a new instruction, mul PS. P stands for parallel, and it's implied that it's SSE. Okay, now here we had registers that were 32 bits wide, or on 64-bit architectures, 64 bits wide. But here we have registers that are 32, 32, 32, or 128 bits wide. So here it's exactly the same operation. Okay, take XMM register 1, multiply it by register XMM 0, put the results back in 0, except It's not 128-bit multiply, it's 432s. So there we go. The red, of course, they're not really red, but this 32 bits gets multiplied by these 32 bits and the result gets put back here. So these four pairwise multiplies all happen at the same time. And that's the beauty of the SSE instructions. I think of it like this. Yeah, okay, I could make one piece of toast in one instruction. I could make four pieces of toast in four instructions over here. Or I could make four pieces of toast in one instruction over there. You know, everything comes down to food analogies, right? All right. Now, for loops are sort of what SIMD can replace, or they alter the for loop. Okay, just like in OpenMP, there are requirements for a for loop to work turned into SIMD instructions. All right, if there are nested loops, two nested for loops, the one to vectorize must be the inner one. There can be no jumps or branches. Um, like jumping around, getting out, breaking out, masked assignments. And in English, what that means is an if statement controlled assignment like this. If a of I greater than 0, b of I equals 1. Those are okay. It can handle those. The total number of iterations in the for loop must be known at runtime when the loop starts. That's the same requirement as in OpenMP. It needs to figure out how many of things it has to do. There can be no interloop data dependencies. Same problem as in OpenMP. This is perfectly legal C, and it's the kind of thing we do all the time in a non-multi-core world, in a non-SIMD world, but you can't do it in multi-core and you can't do it in SIMD. Okay, and it really helps performance if the elements have contiguous memory addresses. That is, if this pair of floating point numbers is immediately following that pair. Okay, this all sounds great, right? All right, what's the catch? The catch is compilers have not yet caught up to producing really efficient SIMD code. That's really too bad because we like to write in standard C and hope the compiler can interpret it for us and produce the best code possible. Right now, that's not happening. The way you can get the best speed up using SIMD is to use assembly language. That's the bad news. The good news is you don't have to write it. Your project 4 will use it, and it has to use it on Flip or Rabbit, but you don't have to write it. We'll give it to you. Okay, and there's two assembly functions. One will be A of I times B of I. The other will be summation of A of I times B of I. Okay, again, these two functions we're going to give you in assembly language only work on Flip and Rabbit. Do not try them somewhere else. It won't happen. Here is SIMD_mul. This takes an A array, a B array, multiplies them together, puts them in the C array. Okay, now the very first thing it's going to do is find out how many multiples of 4 it has. So for instance, if you passed in the length of the arrays is 9, well, then it's going to figure out it has two groups of 4. Okay, and it's going to do those two groups of 4 in assembly language, and then anything that's left over, which if it was a group of 9 would be 1, it's going to do in straight C. Okay, because we can only do 4 pair multiplies in SIMD. This code here is to get A, B, and C into the registers. And this is, by the way, many compilers, including G++, will handle this. If you say underbar ASM, and then parentheses and these cryptic statements there, it will just drop that assembly code. So here it's compiling it into assembly, and here it's just copying it into assembly. So now we're going to do our multiply groups of 4. SSE width is 4. So we're going to just jump down the array every fourth or every group of 4. Here we're moving in A, 4 elements of A. Here we're moving in 4 elements of B. We're putting them in the special XMM registers. We're doing the multiply, putting it back in 0, and then we're moving the contents of that multiply out into C. And we're adding 16 bytes for floats to the pointers so that we can get to the next group of 4. Okay, that's it. Here it is for multiply and sum. Same thing. How many groups of 4 do we have? Here we're setting up A and B. We don't have a C in this case because we're going to bring back a summation. And we've got the length. Here we're going through groups of 4. We're moving 4 elements of A in. We're moving 4 elements of B in. We're doing the multiply, 4 pairs, and we're adding to the running sum. And then we're advancing the A pointer and the B pointer. Okay, and then we're doing the rest by hand that aren't a multiple of 4. All right, what do you get? If you do this without SIMD, here's what I got. This was on Rabbit. About 125 million floating operations per second. Up here, well, depending on the size, I got upwards of 400. Okay, so yeah, this is clearly faster. Now, someday we will all be able to avoid assembly language because OpenMP has added a Pragma OMP SIMD. And here's how it works. You put it right in front of the for loop, and then you do in the for loop what you want the SIMD to do for you. And so this is A times B goes to C. But by putting this pragma before the for loop, you're telling the compiler, turn this into SIMD code. Okay, and we can multiply by a scalar too. It'll handle that as well. And here we go. So this is the graph from a moment ago, and this is this dashed line. That's the performance I got with Pragma OMP SIMD. So clearly it's doing something. It's faster than non-SIMD multiply. It's not as fast as SIMD multiply. Someday it will be. Okay, we're not going to use assembly code forever, but for right now we are. There's another option. Intel has something called intrinsics, and it basically is writing assembly code, but not looking like assembly code. So for instance, you can declare a register by saying underbar M128. That's a type, say A. Um, this loads one of those words from memory. This stores into memory. This multiplies, this adds. These correspond exactly to assembly instructions. And so if I was doing the A times B goes to C, here's how I would do it. And notice right here, we're doing the load from the A pointer, the load from the B pointer. We're multiplying the two of them together and we're storing them. See, we're now calling the store function. We're storing them in the C pointer and then we're incrementing the pointers. So, in theory, this should produce the same assembly language that we have. And it almost does. Here's the multiply and sum, same sort of thing, except it's doing an addition. So here it's doing the multiply, and here it's adding into the running sum, and here it's storing the sum out. So I ran this. This blue line is A times B goes to C, and I just did it in terms of speed up. Speed up from no SIMD at all, one-threaded, no SIMD at all. And so, yeah, I'm getting about 2.5 for the summation. I'm getting roughly 2.5 again. Someday we could use these, but right now they're not up to the same performance as the assembly language. So in Project 4, we're going to use assembly language. I really look forward to the day when we can retire the assembly code. All right. Now, here's another trick. It's not like you have a CPU chip and there's one SIMD unit on there. Each core has its own SIMD unit. So if you've got an 8-core CPU, you have 8 SIMD units hiding in there. Well, gosh, what does that mean? If I've got 8 SIMD units, why don't I just try using them all at the same time? Basically combining multi-core and SIMD. And so here's how you do that. Okay, now we're using OpenMP. We're going to call the time. We're going to say pragma OMP parallel. And there's no for out here because we're not parallelizing a for loop. So the moment we say pragma OMP parallel, we have a thread team. And each thread is executing those 3 instructions. They're all executing the same 3 instructions. But this thread right here is going to come back, say, if it's four threads, say, this function will come back 0, 1, 2, or 3. And each thread will have a different value of this thread. The first element of the array is going to be the thread number times number of elements per core. And the number of elements per core is going to be the total array size divided by the number of threads. So let's say we had 1,024 of an array size divided by 4 threads. That would be 256. Okay, and so if you're thread 0, you start with first equal to 0. If you're thread 1, you start with first equal to 256, and so on. Because these are declared inside the curly braces, they are private variables. Each thread has its own version of these. So each thread has a different this thread and a different first. And then it's going to say, and the ampersand in C means address of, it's going to tell each thread where to start. So thread 0 will start at the top of the array. Thread 1 will start a fourth of the way through the array. Thread 2 will start halfway through the array. So that's what's going on here. Okay, and then SIMD-mul is, well, the assembly code or the intrinsics code, if we were doing that, would be just an address. Okay, an address of A, address of B, address of C, and how many to do. So now we have 4 cores, say, all doing parts of the multiply, and the multiplies are being sped up by SIMD. In theory, these are all independent, right? There's no interference between the SIMD unit and the multi-core. And so we should get combined speed up. Let's see what happened. All right, so we have 4 cores and 4-way SIMD. Here is 16x, and notice we just about hit 16 times speed up. Okay, now we're dropping here, and we'll talk about that in a moment. But basically, this is because it can't bring values in from the cache fast enough to keep up with the speed of what's happening here. This is 2 cores plus SIMD. This is 4 cores alone, 2 cores alone. Yeah, I went a little wild. I'm sorry. I went a little wild with test cases. But the bottom line is, if you look at this, the bottom line is you can combine SIMD and multi-core and get almost a speed up of the number of cores times the number of SIMD, in our case, 4 and 4. So that's kind of cool. Now, why is that dropping? Again, it's working through the array, but it's bringing in 16 floats from memory into the cache line. Then it's going like 4 multiplies, bang, 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 and it's multiplied 16 numbers, and now it has to go get another cache line. So it just can't keep up. The speed coming from memory just can't keep up with what's going on in the CPU. Okay, there is a process called prefetching that if you think that's why you're losing performance, you want to do prefetching. And really what prefetching is, it's allowing the CPU under your control, under your direction, to reach out ahead of where you are in the array and say, start bringing in that cache line that's out here. I don't need it yet, but start getting it. And then by the time I need it, that cache line should be here. Okay. And unfortunately, there is no universal standard of how you ask for prefetching. Okay, it's done differently on different compilers. So yeah, this is what you get. So this is one way it's done, is there's built-in prefetch functions, and PD is prefetch distance, like how far ahead are you reaching? And so I played with this with prefetching. And so blue is SIMD with prefetching. Red is SIMD with no prefetching. So, well, and then green and purple are non-SIMD. Notice if you're not doing SIMD, with and without prefetching makes almost no difference. Okay, because you're not worried about keeping up with getting cache lines. But if you're doing SIMD and then you turn on prefetching, notice the performance you get. And really at this point, if you look at the performance or the speed up or the speed here, the performance here versus the performance here, this really gives you the power of using SIMD. Is if you turn on prefetching, then you really get the full potential, and that's a good thing. Okay, so big takeaway here. SIMD is a way you can speed up by at least a factor of 4 your array multiplications on a CPU. For now, we have to write an assembly language to get all of that performance potential. That won't last forever. Okay, Pragma OMP SIMD will catch up. Intel intrinsics will catch up. And so at that point, we can retire the assembly language and just write in a higher level format. And though prefetching can really help. And in general, that's something you do yourself.